Hi, in this set of lectures we're talking about networks, and in particular we're focusing on three things. We're talking about the logic of networks, which is how they form. Then we're talking about the structure of networks, which is how connected are nodes to one another, how far is it from one node to another node. And then finally we're talking about the function of network. What functionalities does a network have that maybe weren't built in, that just sort of emerge from the structure. Now in this lecture we're going to talk about the structure of the network. So we're going to define a bunch of terms. So we'll define what a network is in terms of nodes and edges, and we'll just define and describe a bunch of measures of networks that help us have a better understanding of how networks differ from one another. So when you think of a network, you can think of a bunch of things that we're going to call nodes, which are points, and then lines connecting those, and those are going to be edges. So a network is really just a set of nodes and a set of edges. Now those edges can be either directed, but that means there's like a little arrow, or they can be undirected, where it's just a straight line. So an undirected node, a network would be something like, the 50 United States. So each node would be a state, and then an edge would just be whether those two states share a boundary, whether they have a common border. So there's no direction there. If Ohio's connected to Michigan, then Michigan's connected to Ohio. In a directed network, then that little arrow that you see, that means that one node points to another node, but it might not necessarily go in the other direction. So if you take a college campus and you ask whether one student looks to another student for fashion advice, it may very well be that person A looks to person B, but person B doesn't look to A. So in a directed network, you could have arrows going in one direction, or you could have arrows going in both directions. So a lot of social networks are directed, but many networks, and the networks we're going to focus on, are going to be undirected networks, just because they're easier to work with. So when I think about structure, we're going to focus on four measures. Degree, which is how many edges each node has on average. Path length, which is how far it is from each node to another node. Connectedness, which is whether the entire graph is connected to itself. And then finally clustering coefficient, which will give us some understanding of like how tightly clustered are the edges. So if A is connected to B and B is connected to C, is A connected to C? Okay, so let's get started. Degree, the easiest one. If you take a node, the degree is just the number of edges connected to that node. So if a node looks like this, its degree is 1. If a node looks like this, its degree is 4. So it's just how many, if you're a social network, it's how many friends do you have. If you're a business and you're looking at, and each edge represents working with another firm, then it's just sort of how many other firms do you work with. So degree is just really a sense of how connected you are to other parts of the node. The degree of a network is the average degree across all nodes. So if I take the entire network and I count up the degree of every single node and then average by the number of nodes, that's what we'll think of as the degree of a network. So a high degree network would be one where lots of people are connected to lots of other people. A low degree network would be one where there's very few connections between people. So here's a network right here. And if I look at this green node, I can ask, what is its degree? And we see that it's connected to 1, 2, 3 people. So the degree of the green node is equal to 3. Now if I want to figure out the degree of the entire graph, you can think, okay, I'm going to go through and count up each person. So this person has a degree of 1, this person has a degree of 1, this person has a degree of 3, and I could go through and count all the way up. Now that seems like that takes a lot of time. There should be a better way to figure out the average degree of a network, and in fact there is. Because all I have to do is count the nodes. So in this case there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. And then I can just count the number of edges. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So 10 nodes, 9 edges. Now each edge connects 2 nodes. So what I've got to do is just multiply those edges by 2. So if I 2 times the number of edges divided by the number of nodes, that'll give me my average degree. So in this case 2 times 9 is 18, divided by 10 gives me an average degree of 1.8. Now when you think of moving along those edges, you can call the people you're connected to your neighbors. So if this is a node here, and he's connected to these 3 people, then these 3 people here are the neighbors of the node. And what we can think about then is people who are more connected have more neighbors. And later on, we're going to extend this concept to neighbors from sort of your immediate neighbors to neighbors who are further away on the graph. Well, here's an interesting result. So we've only introduced one measure, which is degree, and now we're going to get a really sort of fascinating result. That is, the average degree of neighbors of nodes will be at least as large as the average degree of the network. So typically it'll be larger, but it has to be at least as large. What does this mean in less technical terms? It means most people's friends are more popular than they are. So literally it means that if you look at your friends, they on average have more friends than you have. Well, let's see how that can work. So let's look at this network. A has a degree of 2, B has a degree of 3, C has a degree of 2, and D has a degree of 1. So if we add all that up, we get 8 divided by 4 gives us 2. Now we also could have done this by just counting up the edges, which are 4, multiplying that by 2 and dividing by the number of nodes, and that would also give us 2. So what we get is on average, people have 2 friends. Well, now we can ask, what about friends of friends? Well, let's start with D. D has 1 friend, and that's B, and B has 3 friends. Well, let's walk through the whole thing and see how this works. So let's start, again, we saw with D, they have 1 friend, which is B, who has 3 friends. C has 2 friends, A and B. A has 2 friends, B has 3 friends, so that's an average of 2.5. If we look at B, B has 3 friends, A which is 2, C which is 2, D has 1, so that's 1.66. And if we look at A has 2 friends, B and C, and they also have average of 2.5. So if I add all this up, what I end up getting is that this is 9.66 divided by 4, which is, approximately 2.4. So people's friends of friends have 2.4 friends, whereas people on themselves only have 2 friends. What we see is your friends have more friends than you do. That's just a fact about networks. Next measure we want to get to, path length. The path length from A to B is just the minimal number of edges you have to traverse to get from person A to person B, from node A to node B. So if I've got a node here and a node here, but there's no direct path, and to get to those two I've got to take 1, 2 edges, then their path length is 2. So in this particular graph, here's this green node. To get to this green node, I've got to take 1, 2 paths, two edges, so the path length is 2. We can also then compute the average path length for an entire graph. So now you take all pairs of nodes and figure out the path length. So let's take this graph. Let's think of, what are there? There's A and B, there's A to C, A to D, B to C, B to D, and C to D. Those are all the different pairs we could get. So A and B have a distance of 1, A and C have a distance of 1, A and D have a distance of 1, 2. B and C have a distance of 1, B and D have a distance of 1, and C and D have a distance of 2. So if I add all this up, I get 1, 2, 4, 5, 6, 8, and there's 6 total. So that means the average path length is 1 1/3. That's a very short average path length. In that particular graph, it was connected, which is our next measure. A connected graph is just a graph where you can get from any node to any other by walking along edges. So this would be, again, a picture of a connected graph, because you can get from any node to any other node just by walking across the edges. There's also disconnected graphs. So here's a graph where there's 6 nodes, and you can't get from this set of nodes to this set of nodes, so it's disconnected. So in a graph like this, it's interesting because if it's not connected, any information that's over here with A, D, B, and E might not get over to C and F. So disconnected nodes, information's not going to flow between them, which could be a bad thing. Now, if you think about disease, this could be a good thing, because if there's any disease in this population, it's not going to cross this barrier and get over to this population. So depending on what you're concerned with, connectedness could be good or bad. Here's an interesting aside. Remember we talked about Markov processes a couple times. We can think of a Markov process like a network. In fact, our pictures sort of look like networks. So you can think of there being, here's 4 states of a Markov process, and then I can just draw little arrows showing the probability of moving from one state to another. Now this is a directed graph, and it could be that suppose you can get from B to A with probability 0.3, then we could just throw that in. So one way to represent a Markov process is with a network, because you can just write down the states and then draw little directed arrows showing the probability from moving from one state to the next. So again, you start seeing all of our models get related to one another in interesting ways. Last measure, clustering coefficient. This is going to be the percentage of triples of nodes that have edges between all 3 nodes. So if I think of 3 nodes, A, B, and C, it could be that they're connected like this, and then we don't have the full triple. Or it could be that A is connected to B, B is connected to C, and C is connected to A. You get the full triple. So you can fill in the triangle. You can ask what percentage of the possible triangles can you fill in? let's go back and think of a simple graph. So here's a graph, and we can ask, as I start drawing lines, what happens to the clustering coefficient? So if I draw these 3 lines, I can ask how many triangles could there possibly be? And there could be 4. There could be this triangle 1, this triangle 2, this triangle 3, and this triangle 4. But what we see when we look at this graph is that none of those triangles are filled in. So this is going to have a clustering coefficient of 0. What about this graph? Same number of edges, but now we've got 1 triangle that's filled in. So this is going to have a clustering coefficient of 1 over 4. What about this graph? I've got 1 triangle here and 1 triangle here. So this is going to have a clustering coefficient of 2 over 4. And then finally, if I have a completely connected graph, I've got this triangle's filled in, this triangle's filled in, this triangle's filled in, this triangle's filled in. So I have 4 over 4, which is a clustering coefficient of 1. So if you think about networks, you can ask all sorts of really interesting questions. So here's a simple quiz question you might ask. Draw 2 connected graphs, each should have 6 nodes and 6 edges, but have different clustering coefficients. Now the reason we'd ask an exercise like this is to get across the idea that number of edges sort of tell you how connected a graph is, but it doesn't tell you how clustered it is. So it's possible to have 2 different graphs with the same number of nodes, same number of edges, but different clustering coefficients. So here's graph 1, and if we look at it, there's only 1 triangle filled in. So this clustering coefficient is going to be 1 over the number of triangles. Well, how many triangles are there? We've got 1, 2, 3, 4, 6 nodes. And we want to ask, a triangle consists of 3, so that means there's 6 nodes we could pick first, 5 we could pick second, 4 we could pick third, but the order doesn't matter. 3 times 2 times 1 doesn't matter, so that means we get 20 triangles. So this is going to have a clustering coefficient of 1 over 20. Well, here's another graph with 6 nodes and 6 edges, but none of the triangles are filled in. So this is going to have a clustering coefficient of 0 over 20. So 2 graphs, same number of nodes, same number of edges, different clustering coefficients. So what have we learned? We've learned that there's structure to graphs. We can measure degree, which is on average how many nodes is another node connected to. We can talk about path length, which is how far is it from one node to another node. We can talk about connectedness, is the whole graph connected. And we can talk about clustering coefficient, which is how many triangles, or the possible triangles, how many of those are filled in. Now these are statistical measures, so let's talk about why would we care about these? Why might these be important? When you think about degree, what is it telling you? It's telling you the density of connections in a way. It's telling you just how connected is this graph. So you could think of this as some sort of proxy possibly for social capital. So if you looked at a community and there were very few connections between people, then not many people know other people. So remember we talked about Bob Solow saying social capital can't be just this abstract thing. We need some measures of it. One measure could be how connected are people to one another? What's the average degree of the social network? You can also think about speed of diffusion. If there's some piece of information out there, how fast is it going to spread on this network? Well, one thing that will determine that is how connected people are and how many nodes people are connected to. So if somebody's connected to 100 people and you tell them something and they tell all 100, it's going to spread really fast. If I'm only connected to 2 people and you tell me something, then that information is going to spread fairly slowly. What about path length? Why would we care about path length of the graph? Well, think of an airline graph. It's going to tell you the number of flights you're going to need on average. So if you wanted to fly from Miami to LA and the average path length was 1.1 for the airline network graph, you'd know you're probably going to get a direct flight. If the average path length was 7, then you'd know, oh my goodness, this is going to take me a lot of flights to get from point A to point B. It also tells you social distance. So suppose you run an organization and you've got a network and you know that the average path length between employees is 6. That means randomly picking 2 employees, it's going to take 6 other employees or 5 other employees to get from employee A to employee B. That means that information, knowledge, ideas are not going to spread very fast within your organization, and you may want to try and figure out ways to reduce that path length. And last, the likelihood of information spreading. If the path length is really long, it's just not that likely that information is going to make it 9 steps, 10 steps, 11 steps if people are that disconnected. What about connectedness? Our next thing. Well, connectedness for Markov processes, it matters. Remember, in a Markov process, you had to be able to get from any state to any other state. If the nodes are the states and it's not connected, then we can't apply the Markov convergence theorem because that was one of our assumptions. You can get from any state to any other. If you think about the abilities of a terrorist group, you might say, okay, here's all these people who are really upset with the world in some way, and they're sort of a terrorist organization. There's people who want to carry out some tasks that maybe we don't want them to carry out. If their network is not connected, then it's going to be difficult for them to carry out these activities. If it is connected, then they can pass information, they can possibly carry things out. So things like path length, degree, and connectedness are going to determine the functionalities of organizations that do good as well as organizations that do bad. Now, connectedness also matters if you think about things like the internet or power failures, the electric grid. If the electric grid becomes disconnected, if you get disconnected from the grid, then you don't have any power. And finally, if you think in terms of information, if people are disconnected from other people, they can be isolated in terms of information, so they may not learn things or may not figure things out. And then finally, the clustering coefficient. Clustering coefficient can be used to figure out how redundant or how robust the network is. So if you pulled one person out, so think about it, if I get a little triangle here between A, B, and C. If A gets wiped out for some reason, B and C are still connected. So it gives you a sense of how robust or how redundant the network is. This is also sometimes used as a measure of social capital, because it means that there's just these tight links between people. Then one last really interesting thing about the clustering coefficient, it can be used to capture how likely an innovation is to be adopted, in particular, possibly a new word. So if I've got three people that are all connected, A, B, and C, and A uses some new word, and B hears it and then tells it to C, and then C uses the same new word and A hears it, you get this sort of autocatalytic set where the information gets even passed through the loop, and it now seems part of the new normal. A says, well, I said this, and now I heard C say it, so this must be something that people say. Whereas if A wasn't connected to C, when A said something new, it could just sort of fan out, and it may never come back to A, and so A may be less likely to maintain the innovation. So these clusters, by creating feedbacks, can allow things to be maintained within a network. One last thing, I've introduced all these measures. There's still a sense with networks that a picture is worth 1,000 words. And one reason I think for the rise of networks so much is because of the fact that we now can graph these networks in really interesting ways. So let me show you the power of pictures. Here are three graphs. The first one is the 50 US states, and there's an edge, those are the nodes, and there's an edge if they're adjacent. The second one is a group of 48 universities, and then it shows there's an edge between them if they play football against each other. So these are American universities. And then the last one is an airline, so each node is an airport, and a network edge is just going to be whether the airline flies from that network to another one. Here are the statistics on those three graphs. So graph 1 has a degree of 10.8, a path length of 4. Graph 2 has a degree of 9, a path length of 6. Graph 3 has a degree of 10 and a path length of 4. So they're all about the same. So if you look at these statistics, there's not a huge difference between the three networks. Let me show you the pictures. Here's graph 1. What do you think this is? Well, this is clearly an airline network. There's a couple hubs here, and there's all these cities that the airline flies into. Here's graph 2. What is this? Well, this is the 50 United States. Up here are Alaska and Hawaii, who are disconnected, and it looks, in fact, a lot like the United States. And then here's graph 3. These are the football conferences, 1, 2, and 3. And what you can see is the teams all playing each other within conference with an occasional game outside the conference. So what we see is we see very different structures between the airline network, the states, and the universities playing football, even though the statistics, the first two statistics, degree and path length, were about the same. Now, where we would see a difference statistically is in clustering coefficient. So if we look at this graph, the clustering coefficient is going to be very low. In fact, it's going to be 0 almost. There's very few triangles in this graph. In graph 2, there's a little bit of a clustering coefficient, but in graph 3, the clustering coefficient is really high. So the sense in which maybe instead of saying a picture's worth 1,000 words, we might want to say a picture's worth at least 3 statistics, or maybe 4 statistics, because you need quite a few statistics before you can really start distinguishing between graphs. So degree won't be enough, path length won't be enough, but if you throw in clustering coefficient, then maybe you start making more sense of the graph. Okay, so that's structure. We now understand that we can think of networks as having nodes, edges, degrees, path length, being connected, and then also having these clustering coefficients. So this gives us a language for describing different network structures. What we want to do next is talk about the logic through which these networks form. All right, thanks.